Hello, Royals. For lesson 3.2, I just wanted to go through a couple of examples with you because rationalizing is something that can be a little bit different to what we're used to. We need to be pretty strong with fractions. We need to review how to manipulate radicals from quadratics. It is something that I expect you to be able to do by hand to show your work with, and again, not depend on a calculator. And it's also dangerous to just sort of memorize what's going on and not develop an understanding. Let's take a look at example 5b. We're asked to rationalize the denominator and simplify. So I've got 7 root 3 over 4 root 5. So we would say that this denominator is irrational because 4 times the square root of 5 is an irrational number. I can do something about that. I can manipulate this fraction, just like I can convert a fraction to find a common denominator, but I don't want to change its value. What I do then is I make sure that I multiply by 1. I'm not multiplying by root 5. If I multiply by root 5, that's going to change the value. I want to multiply by 1. I'm not interested in multiplying by the denominator by 4 root 5. If I multiply 4 by 4, that'll just make it larger to 16. Then my numerator will become 28. I'd have 28 16ths, which reduces to, guess what, 7 quarters. Makes absolutely no sense to multiply by 4 root 5 here, but lots of students do it because they just memorize to multiply by the denominator, I guess, which is false. I don't like the irrational part, so I'm going to multiply by the irrational part, but I need to multiply by 1. Now what I'm doing here is I'm multiplying the numerator by 1 root 5 and the denominator by 1 root 5. Let me show a few more steps than the example in the printed note. I now have 7 times 1 times root 3 times root 5. 7 times 1 times root 3 times root 5. I'm choosing to change the order of a multiplication because the order of a multiplication doesn't matter. I have 4 times root 5 times 1 times root 5. That's 4 times 1 times a root 5 times a root 5. Okay. 7 times 1, that's just 7. And root 3 times root 5, that's the square root of 3 times 5. That's a property we learned back in quadratics. 4 times 1, that's just 4. Root 5 times root 5, that's just the root of 5 times 5. Again, I'm taking this very slow so that I don't develop any bad habits about going too quickly. You'll want to develop some speed here in a bit, but let's see. I've got a 7 in the numerator. Root 3 times 5, that's a root 15. And in my denominator, I've got a 4 times a root 5 times 5. 5 times 5 is 25. My goal here, though, was to rationalize my denominator, and I still have a radical symbol, but I have a radical symbol on a perfect square radicand. I didn't know what the square root of 5 was. I could estimate it, but I do know what the square root of 25 is without using a calculator. That is going to be 5. And then I can just tidy things up here and do 7 root 15 over 20. I see, do 7 and 20 share any factors? The answer is no. 15 and 20 share a factor, but this isn't a 15, is it? That's a square root of 15. The square root of 15 doesn't have any perfect square factors, so I know that I'm in simplest form. Now, this can go much faster. You could go from here, you show your step, of course, and then do 7 root 3 times root 5. Well, that's going to be, 7 root 15. And then you could say, well, root 5 times root 5, that's root 5 squared, which is going to be 5 times 4 is 20. Sure, you could go fast like that, but often students that memorize, oh, root 5 times root 5 is just 5, they don't really know what is going on. Okay. Rationalizing binomial type denominators. Let's go to example 6, and we might go through all of them. We'll see how we're doing. I am given the expression 3 over root 2 plus root 5. And maybe I should illustrate some of the things that could go wrong here. So sometimes students say, all right, well, I'm going to rationalize the root 2. So these are bad ideas. I'll change colors. I'm going to rationalize the root 2. I'll just multiply by root 2 over root 2. And you're allowed to do this. You just don't want to. When I multiply the denominator by root 2, I have to use the distributive property of multiplication. I can't just cancel the square roots and root 2 times root 2 magically becomes 2 and the root 5 doesn't change. So what I would end up with is root 2 times root 2, that's going to be 2, plus root 2 times root 5, that would be root 10. It's equivalent. I haven't done anything wrong yet, but I haven't really done much right either. Then I might say, all right, well, I'm going to rationalize this root 10 now by multiplying by root 10. I'm not allowed to only multiply the plus 1 root 10 in the denominator by root 10. If I multiply by 1, if I multiply the entire denominator by root 10, I have to use the distributive property of multiplication, which means I would end up with, let's see, this would be a 3 root 20, which can now be simplified. I'm making things more complicated. This root 10 times 2 would be 2 root 10, and then I would have a root 10 times a root 10, which is a root 100, which is going to be 10. You might notice you could keep on doing this, and your irrational part is just going to keep skipping backwards and forwards and backwards and forwards. So that's not what we want to do. What we want to do is use the idea of conjugates. And let me just review conjugates with you outside of radicals. Let's say that the conjugate of x minus 5 is x plus 5. These two expressions are conjugates of each other. They're not opposites. The opposite of x minus 5 would be 5 minus x. When we multiply conjugates together, we get a difference of squares when we had natural coefficients here. We'll have an x times an x times a 5, a negative 5 times an x, and a negative 5 times a negative 5. And when I multiply those conjugates, the reason why I get a difference of squares is because my interior terms will eliminate through addition or subtraction to 0. And I'm left with the square of the first term minus the square of the second term, if I want to think of it that way. You can use conjugates with these radical expressions. They're just called radical conjugates. And this is how we are to rationalize binomial type denominators. I would have a hard time estimating where the number 3 divided by root 2 plus root 5 is on a number line, because I would have to approximate root 2 and approximate root 5 and approximate that sum and then approximate the quotient. I don't like having an irrational denominator, and I was told to rationalize the denominator as well. So what I do is I multiply by 1. I multiply by 1 in the form of the radical conjugate of the denominator. Another conversation that I would normally have in class, that's difficult to have in the lesson, is talking about what we should do in the numerator. You might want to start off by just doing your work in your denominator, though. That's where all the interesting stuff happens. So I think I'm going to do that. I'm going to do like a couple of steps just in the denominator. I'll leave room to write in my numerator. In my denominator, I am going to have, and this is again where memorization can cause problems. If you're you practice this a lot, you'll probably be able to tell me that my answer down here is going to be 2 minus 5. But then when we have to expand in the numerator, students that memorize that, it really falls apart for them. I don't think you're not going to be doing 20 of these questions on any one assignment. So you want to take your time to show these steps. I'm going to distribute these two terms through these two terms here. I'm going to have root 2 times root 2, root 2 times negative 1, root 5 times root 2, root 5 times root 5. Let's maybe do this a little bit faster than that first time up in example 5b. Root 2 times root 2, that's going to be root 2 times 2, that's root 4. Root 2 times negative 1 root 5, that's going to be negative root 10. Root 5 times root 2, that's going to be plus root 10. Negative root 5 minus root 5, that's going to be negative root 25. Let's continue down here, focusing on our denominator. I know the square root of 4, that's 2. I don't know what the square root of 10 is. It's like 3.1 or something like that. But I know that negative 1 root 10 plus 1 root 10 is going to give me 0 root 10s, eliminating the irrational part. And then I'm going to subtract whatever the square root of 25 is. I know what the square root of 25 is. And I think you'll find it nice to just concentrate on your denominator. It'll also give you a reason for knowing what to do in the numerator. The question usually comes up in class, how do I know whether I should expand this or not? And I would ask you, well, why would you want to expand the numerator? It doesn't cause any simplification. Expanding is not the same as simplifying. And I can tell now by using foresight, by looking ahead, look, my denominator has a factor of 3. So wouldn't I want to keep this factor of 3 out front so that on maybe this step, I'll be able to divide a factor of 3 out from the numerator and denominator? I think so. So turns out that I actually don't really want to do anything in my numerator. I'm just going to write it as a multiplication. And then when my numerator when my denominator catches up with my numerator all the way over here, now I see I have a factor in my numerator and my denominator. And you should feel like we are doing the first part of Unit 1 again, that we're simplifying rational expressions. And we simplify rational expressions by dividing factors from the numerator and denominator. Like in grade 9 and like in the first half of Unit 1, we don't want to leave that negative coefficient in the denominator, so I'll move it out front. And I believe another optional solution in the lesson was maybe distributing this negative through and changing the order, or treating this as the opposite of root 2 minus root 5. The opposite of root 2 minus root 5 is root 5 minus root 2. I've just distributed and rearranged there. Okay. Let's try C together. You can do B, you can do the homework, you can check the solutions to the homework, and then always message me if you have any specific concerns. Let's look at C together because it's algebraic and there's a problem here that often happens. So we're given this algebraic expression and we are told to rationalize the denominator. It's a binomial type because I have the two terms here. I can't rationalize this by multiplying by root x. I can't rationalize it by multiplying by root 3 plus x. I want to multiply by 1 in the format of the radical conjugate of the denominator. Now the conjugate of root something minus root something else is root something plus root something else. Notice I didn't change something else. This 3 plus x has to be 3 plus x here. You're not changing that sign. This even that shouldn't be a fact that you have to memorize. It's something that will make sense when we expand. This is another case where I shouldn't expand in the numerator. Take a look at example 6b. You'll see that we choose to expand in the numerator because it causes simplification. I'm still going to concentrate on the denominator and let my numerator catch up. So I'm going to be multiplying this binomial by that binomial. I'm going to do this times that, this times that, this times that, this times that. Root x times root x squared. Don't be in a rush. Root x times root 3 plus x. I'm going to choose not to distribute because I know what's going to happen with these expressions. Let's just write it as root x times root 3 plus x, or positive 1 root x times root 3 plus x. Then I'm going to have a negative 1 root 3 plus x multiplied by a positive root x. That's going to be minus a 1 root x root 3 plus x. Notice I just reversed the order of the multiplication. I'm a little short on space here. And then I'll have a product here. I've got a negative 1 times a positive 1 and a root 3 plus x times a root 3 plus x. Well, negative 1 times positive 1 is negative 1. And then I'll have the square root of 3 plus x all squared. And I'm going to argue here again that I don't want to expand that. If you ask me what is the square root of 9 plus 6x plus x squared, I would want to write it as a factored form. Let's leave this as a factored form because of our purpose here. We're trying to simplify. Okay, the square root of x squared is x. Now, this weird expression, positive 1 root x root 3 plus x. You could write it as the square root of 3x plus x squared, but we don't care about doing that because we have whatever we have here, we have its opposite here. It's being subtracted. So try reading it in English. 1 root x root 3 plus x minus 1 root x root 3 plus x gives me 0 root x root 3 plus x's. And I don't announce terms that I have 0 of. Now here is the most common mistake. We want to subtract whatever the square root of 3 plus x squared is. Well, the square root of 3 plus x squared is going to be 3 plus x. We just need to make sure that we subtract 3 plus x. And that is not what I've done. I have subtracted 3, and then I've added x. So I wonder if maybe even back on the previous example, I should have just drawn in some brackets to say that I'm doing 2 quantity minus 5 quantity. Were they necessary here? Nope. Are they necessary on this x? Nope. Do you need them on this 3 plus x? Oh, yes, you do. You betcha. That's going to change our answer significantly. When I end up having x, I want to subtract 3 and I want to subtract x. That actually eliminates the variables from the denominator. Now, my numerator has some catching up to do, and it can be frustrating that you're actually, in most cases, doing nothing with your numerator. Yes, you do need to write it out every single time. Sometimes students write like ditto, or they write an asterisk, or those little quotation marks that means repeat whatever. Those aren't math symbols. If having to write this out is the worst part of your day, doesn't sound like a bad day. And like before, hey, look at that. I have a factor of -3 in my denominator, and is there a factor of 3 in my numerator? Yup. Let's divide those out, leaving me with 3 times root x plus root 3 plus x. Okay. Lots of practice on the worksheet, which you might want to print out, but you could always just look at the examples and write them out on there. There, as always, are solutions to worksheets on our website. And like I said, message me if you want to see any other examples of this. It doesn't happen a lot in our course, but it doesn't go away either. You'll be doing a bit of rationalizing and advanced functions and calculus and vectors. Okay.